let's welcome him. And the floor is yours, sir.
All right. Thank you so much for having me. Please, can you confirm that you can see my screen?
Yes, I can see your screen, Doc.
Okay, yeah. Thank you so much. Hi, everyone. As you've heard, my name is Michael, and today I would like to talk about developing affordable bio-implant alloys for developing countries. There are lots of materials out there, but I strongly feel that lightweight stainless steels could be the answer. And it's quite interesting to listen to other speakers alluding to how resilient and versatile steel can be as a material. I don't work alone. This research started in my small group in 2021 without a lot of funding. So I've got a few undergraduate students who assisted with the research then, and here are the pictures. And of course, I've got Dr. Klenam also supporting the research as well. So without wasting too much time, we all know that due to technological advancement, we're living longer these days, which is a good thing, but it's also a potential threat to our general well-being and our good health, especially when we think of the future. So by 2030, geriatric population would have reached 1 billion, 1.4 billion. Then by 2050, the population of the world would be around 2.1 billion, and people who are older than 60 years would be around 1.7 billion. And one thing comes with old age, the susceptibility to bone fractures and you becoming disabled. And if one person in the family becomes disabled, it affects everyone. So that would really affect our general well-being. And 2050 is not very far from here. So we really need to find a way to address this problem. Yeah, there are current ways to solve it. The best procedure is the surgical method, but it's quite expensive because titanium, which is considered the gold standard material for making implants, is very, very expensive. And you can see the breakdown of the cost of going through a surgical treatment. What is really concerning to me is that by 2050, 80% of older adults will live in developing countries. No single African country is considered as a developed country. So which means we'll have a lot of older adults. Can they all afford titanium? I don't think so. Over the years, I've been working on reducing the cost of titanium alloys, basically. But I think that if we do not find cheaper ways other than process to beneficiate titanium, we're not going to have, implants that can be afforded by, poor population or people who are earning, quite low. So I think that we need to find cheaper implants. Apart from titanium, there is an alternative material called 316L stainless steel that are used as implants. I had recently, I really confirmed that, and while engaging with an orthopedic surgeon, that the 316L stainless steel is not even being approved in South Africa hospitals anymore. And that is because it's highly dense and it causes other problems when used as implants. So we need to find alloys that are cheaper than titanium and at the same time less than 316 stainless steel. So do we think we can find this alloy? I thought probably low density stainless steel could be this alloy. People have created a lot of narratives about steel. It's dying, high entropy alloys are taking shape and stuff like that. But I think the versatility of steel has made it relevant and it will continue to be relevant. So, but I want to give you an overview of, low density steels in general. It was first reported in 1930 by Cotter and Ton. In 1930 by Cotter and Ton, actually. Then in 1958, basically, and Karen actually then thought about, adding, replacing chromium and nickel in stainless steel with manganese and aluminum. Between 1930s and 1950s, there was not a lot of research carried on. But of course, the motivation for creating low density steels in 1958 is to reduce the cost of stainless steels because chromium and nickel are quite expensive. And things went quiet until the 2000s. And in the 2000s, because we want to reduce carbon footprint, we need lighter material, lighter alloys that would result to energy efficiency, less consumption of fuel, and lower emissions of carbon and other greenhouse gases. So these alloys then sparked the interest of many researchers. And that was when we really developed the metallurgy of low density steels. The key alloying elements are manganese, aluminum, and carbon. When you introduce manganese, you reduce the density of the alloys as well as the elastic modulus. But more importantly is aluminum. More important is aluminum because it has very low density. So when you had aluminum to iron, you reduce the density quite a lot. As you can see, you can obtain 1.3% reduction in density for 1 weight percent of aluminum that you had. But disadvantage is that there's 2 weight percent reduction in the loss. And this is probably the reason why we don't have any low density steel still used in the automotive industry. But of course, adding high amount of manganese and aluminum to iron and controlling the amounts of carbon could give you high plasticity and high strength. The strength comes from the different types of carbides that precipitates within the grain boundaries. And some also precipitate around the grain boundaries, but it's more beneficial if the carbides precipitate within the grain boundaries. In terms of plasticity that we have, that is even much superior to high strength alloy steels, is because of mechanisms such as twinning-induced plasticity and then shear band-induced plasticity and microband-induced plasticity. So, but despite the fact that we have good plasticity, high strength, reduction in low density, that all the alloys that were developed around then had poor corrosion resistance until 2020, when Moon thought, okay, it would be nice to add a little bit of chromium or nickel or combination of the two to FEMNALC systems, and he was able to arrive at a set of alloy that has between 3 to 5% of chromium, and that gives improved corrosion resistance than most of the stainless steels that are already in the market. So that paper was published in scientific reports, Nature. So we thought that, and he was the first person to actually MNALCRC system, low density stainless steel. If this alloy has very low Young modulus, it's not lower than that of titanium. If it has reduced density and we can improve the corrosion resistance, we might be considering it for biomedical application by making implants from there. And to do that, one of the first tests you want to do is corrosion. I'll talk a bit more about some of our experimental procedure. But why we're interested in this class of steel? It's because South Africa is the largest producer of manganese in the whole world, and manganese is an element added to these grades of steel. You can have up to 30% of manganese in that steel. So last year, in 2022, South Africa produced 7 million metric tons. And South Africa has the world's largest reserve of 640 million metric tons of manganese. So this is something that we really need to start looking at. The idea of using low densities in the automobile industry is really, growing in Europe, but in Asia, they're considering it for, storing or transporting, gas, liquefied gas. But basically, we thought that if we could make it applicable in the biomedical industry, it would serve a much purpose, especially the fact that we have manganese in abundance in Africa. Apart from South Africa, Gabon is the second largest producer of manganese in the world. So I think this is something that we need to tap into, and we can create another success story like that of CCR12 alloy if we continue working on this over time, especially if we can develop this material for a commercial-based application, which we think that maybe the biomedical application would be an interesting one. So now let me give you some of the give you an overview of the, preliminary experiments we carried out. We looked at alloy in this composition, different alloys in this composition range, and we carried out thermocac analysis to just do phase predictions, and then we did melting, and then we tried to do spark analysis to come up with the composition, because when you're producing these alloys, aluminum easily evaporate, especially when you're producing via casting. So you need to really be sure of the composition that you're arriving at. We did microscopy and XRD analysis to establish the phases, because depending on the alloying elements, the amount of the alloying elements, you could have, different grades of low density steels or low density stainless steel. And after we did this, we got some results, and that results made us consider carrying out thermomechanical processing, which I would also talk about. So let me just give you a few of the results that we've obtained. So in 2021, when we started, what we tried to do was to test the cast alloys in simulated body fluids, carrying out corrosion on them. And I'm just showing you one of the many results that we obtained, but this table is what is more important. If you look at the 316 L stainless steel that we used as the base material, it's a commercial grade, mind you. Now you see that the low density stainless steel grades has corrosion rate that is 10 times lower than that of 316 L stainless steel, and this is just in the as cast form, both in Angst solution and of course in 0.98% NaCl. These two solutions are considered simulated body fluids basically. So that was quite interesting. Yes, from the curves you will see here that in terms of corrosion potential or ECO, the 316L is superior. But I learned from Prof. Sanderberg that what is most critical is the corrosion rate, because when corrosion starts happening, how fast is it happening? And that's what we want to focus on. So we thought that this is quite good. And considering that this is a commercial grade alloy and we were just, testing the as cast sample, we thought that having this corrosion rate was quite beneficial. It's 10 times lower than that of 316L stainless steel. But we found something quite interesting. We saw that in the low density stainless steel, there are lots of pitting, because the pitting occur in the dendritic region. So you have the carbides and the matrix forming the dendrites, and I think the chloride ion attack the interface between the carbides and the matrix. The matrix could be a mixture of ferrite and austenite or externite, depending on the amount of manganese and aluminum and carbon that you had. So we saw this, and we thought if we try as much as possible to subject this to thermomechanical processing, we can get rid of the pitting. But how that affects corrosion rate, we didn't know. So what we did next was to carry out thermomechanical processing using optimized parameters. Popularly reported temperatures and strain rates for deforming this grade of steels based on literature. And we found that, and after that, we carried out, corrosion testing again on the deformed sample to see if there is any difference in terms of reducing the pits, and of course, maybe eliminating the pitting that we find in the dendritic region. And this is just a typical as cast dendritic microstructure, and I'm giving you an example of two different alloy systems among the wide range of alloys that we produced. And you can see this dendritic configuration in both cases. And when we carried out thermomechanical ferrite here, and some global ferrite as well.
Hi, Doc. You have 1 more minute. Can you wrap up?
Okay.
Yeah.
All right. Okay. Thank you so much. And what we see is through thermomechanical processing, we were able to, change the microstructure. But does this affect the corrosion results? And you can see that in this case, when we use this particular, parameter, we were able to find, results that are nearly reproducible. And in terms of the, calculating the corrosion rate and ECO as well, we see that for this same parameter, it's quite close and standard deviation is quite low. when we use strain rate that is much slower, the results are not necessarily reproducible, which shows that there are some variations in the microstructure and we need to optimize the thermomechanical processing parameters. But for these conditions, we still see that the corrosion rate was 10 times lower than the 316L stainless steel, and of course was lower than the maximum permissible corrosion rate for bio-implant alloys. So we looked at the microstructure of those particular samples, and we could see that we were able to, reduce the effect of pitting, and this is another microstructure of, confirming that. And what have we learned so far? What we've learned so far is that maybe low density steel might be a promising material for bio-implant application. We could improve the microstructure through thermomechanical processing. But of course, it's crucial for us to still optimize those parameters. And this is what we are currently busy with. Thank you for having me, and thanks for listening.
Thank you very much,